Hello everyone. In this video, I'm going to cover the topics from week 11 of the course. This is our last week in our trees unit. We're going to cover priority queues and implementing a priority queue with a heap. The reading for this week includes Miller and Raynham section 6.8 through 6.10 and the participation activities in SciBooks sections 4.11 and 4.12. So let's get started with lesson L11-1. The learning objectives for this lesson include understanding what a priority queue is and implementing a priority queue with a heap data structure. A priority queue is a queue that orders the items in the queue by their priority. The item with the highest priority is at the front of the queue, and the item with the lowest priority is at the back of the queue. If a very high priority item is in queued, it will be stored toward the front of the queue. It will also be one of the first items dequeued from the queue. If it becomes the highest priority in the queue, it will be stored at the front, and it will be the first item dequeued from the queue. So here's a nice diagram here that shows several different items being enqueued or inserted into a priority queue. When we go to dequeue an item from the priority queue, we're going to delete the minimum. In this case, a smaller value is denoted as a higher priority. So this is going to dequeue the next element with the highest priority. We could adapt our queue code from several weeks ago to be an implementation of a priority queue. We could enqueue items into the queue in sorted order. Such an algorithm would be linear for inserting items and constant time complexity for removing the highest priority item. Here are a few other data structures that we could use to implement a priority queue. An unordered linked list. We could have constant time complexity for insertion, just insert at the head, but we'd have to do a linear search in order to find the item with the highest priority. So this would be time complexity big O of n. Ordered linked list is going to flip these time complexities. For insertion, we're going to have to find where are we going to insert this item in a sorted linked list. For removing the highest priority item, this will be constant time complexity because it'll always be at the head of the linked list. A balanced binary search tree can give us logarithmic insertions and highest priority removals. And we're actually going to explore a special binary search tree today called a binary heap that supports inserting and removing items with logarithmic time complexity. So let's talk about binary heaps. A binary heap is a binary tree with two properties, the structure property and the order property. We'll talk about more about each one of these properties here shortly. A binary heap is going to be implemented as a balanced binary tree in order to keep enqueue and dequeue operations logarithmic. A binary heap is usually a min heap or a max heap. A min heap maintains the smallest items at the front of the queue, whereas a max heap maintains the largest items at the front of the queue. We'll derive the interface and implementation of a min heap, though you can imagine the implementation for a max heap is going to be quite similar to a min heap. Now for the binary heap structure property. We'll keep the heap balanced by creating the heap as a complete binary tree. Each level in a complete binary tree is full except for the bottom level of the tree. So for example, in this complete binary tree, we see every level is full except for the lowest level. Now the lowest level will be filled from left to right. So as you can see, each possible slot in our lowest level is filled from left to right. If we were to increase the size of this tree by 1, we would have to have a node here because this is the next available slot. The height of a complete binary tree with n items is floor of log base 2 of n. While we can store a complete binary tree, such as this one, using nodes and links, we can more conveniently store it as a single list using indices and offsets. So let's see how this can be done. Let's let a parent node P, so this would be a node that has children, be at index I in the list. The left child of P is going to be at 2 times I, and the right child of P is going to be at 2 times I plus 1. So for example, A is a root node and it has children, B and C. So A is going to be stored at index position 1. This is our I in our example. 2 times I will tell us where the left child of A is. So 2 times 1 is 2. So the left child of A is at position 2, which is B, and we see that in our graph here as well. or in our tree diagram here as well. The right child of A is going to be at 2 times 1 plus 1, which is 3, and here is C. Now, if we need to find the parent of a node in our list representation, the parent of any node n, where n is at index I, is going to be at I integer divide 2. So for example, let's take a look at J here. J is at index position 10, so 10 integer divide 2 is 5, which tells us that J's parent is at index position 5, which is E, and if we look in our diagram, we do see that J's parent is E. And here's another example here showing colored arrows denoting the child links and the parent links. Now, one thing to note is we do not store any node at index position 0. This is so our integer arithmetic up here is going to work out nicely for 2 times I plus 1, find our children, and to find our parent using integer division. One thing I would like to note before moving on from the structure property to the order property is since the list stores a complete binary tree, all nodes past the halfway point in the list are going to be leaf nodes. This is going to help our implementation of our binary heap be quite efficient. Let's talk about the heap order property. In a heap, for every node x with parent node p, the item in p is smaller than or equal to the key in x, and this is for a min heap. A tree that upholds the heap property will always have the smallest item in the root node. So here's an example here. So 5 is our root node, so everything below 5 in our tree should be smaller than 5. And looking at these nodes, we do see that 5 is the smallest item in the tree. Now this is going to be true for every subtree in the heap. So for example, the subtree 9 is the root node. All nodes below 9 should be smaller than 9, and we see that is the case. Now, this is not a binary search tree because the items are not ordered from left to right. For example, not all items on the left side of 5 are going to be smaller. That is definitely not the case. One thing I'd like to note before moving on to common binary heap operations is duplicates are allowed in a binary heap. Just want to make sure that it's clear that no order is implied for elements which do not share ancestor-descendant relationship. So our duplicates here will not share our ancestor-descendant relationship because they will be equal. Moving on to common operations associated with binary heaps, we'll be working with min heaps for all of these examples. We're going to cover insertion into a min heap, deletion from a min heap, specifically delete min, and then we're going to talk about building a heap from a list, a heapify operation. To insert a new item into a min heap, we're going to insert the new item into the heap at the next available slot or hole in the complete binary tree. This is going to maintain our heap structure property. However, this is also possibly going to violate our heap order property. So then we're going to percolate, which is going to be like bubbling up the element, bubble the element up the heap while the heap order property is not satisfied. So this is going to be an effort to restore the heap order property. So let's take a look at an example. Here we have a tree here and we want to insert 14. So we're going to insert 14 at the next available slot in the heap. So this is a complete binary tree. So we're going to fill the bottom level from left to right. So the next slot is here. We're going to insert 14 at this location, the right child of 31. Now, as I said before, this maintains our heap structure property, but it violates our heap order property. So now we need to restore the heap order property by percolating 14 up until it reaches a position that does not violate the heap order property. So we're going to compare 14 versus 31. 14 is less than 31, so we're going to swap these. Now 14 is the parent of 31. And we're going to continue checking, do we need to keep percolating 14 up? So now we need to find out, is 14 smaller than 21? Yes, it is. So we swap 14 and 21. 14 is now here. Now we're going to test, is 14 smaller than 13? It is not. So we are going to stop percolating 14 up, we found a location for our new item 14 that maintains the heap order property. And these dashed lines here show the path of percolating 14 up. Now let's talk about removing the item with the highest priority in the priority queue. This is going to be a delete min operation. So when we want to dequeue from the priority queue, we will delete the minimum item from the min heap. The minimum item will always be at the root node, so all we have to do is remove the root node. However, we of course need to maintain our complete binary tree. So we'll decrease the heap size by 1 to denote that the size of this heap is going to decrease. And then we're going to grab the last item in our list. So this would be in our bottom level, the most furthest right leaf node. And we're going to insert that as our new root. Now, this is going to maintain our heap structure property, but it's going to violate our heap order property. So we're going to percolate this new root node down until it finds a location where the heap order property is satisfied. So let's take a look at an example. Here's a tree here. We want to delete 13. So we're going to whack 13 out of here, and we're going to move 13 up to be our new root node. So 13 is now our new root node, and we're going to percolate, 31. 31 is our new root node. We're going to percolate 31 down, which you can think about it as doing kind of pairwise comparisons and bubbling it down. So let's check. Is 31 greater than the smallest item in either one of his children, 14 or 16? Yes, it is. So we're going to swap 31 with the smaller of its two children, which is 14. So now 14 becomes the new root node. 31 is the new root node, 14's left child. And now we're going to do a similar comparison while we percolate. Is 31 greater than the minimum of its two children? So the minimum of 19 and 21 is 19. So is 31 greater than 19? Yes, it is. So we're going to swap 31 with 19. So now 31 is the left child of 19. And now we're going to ask, is 31 greater than the min of its two children? The min of its two children is 26. And 31 is greater than 26. So we're going to swap 31 and 26. And now we're going to stop because 31 is a leaf node. There is nowhere further we can take this on our percolation path. So the dotted line here shows our percolation path, and we do have our heap order property restored and our structure property maintained. Now the last operation we're going to talk about is build heap. So suppose we have n items and we need to build a heap from these n items. We would call this heapifying the list of n items. So there are a few ways we could do this. The first way is we could initialize an empty heap and perform n inserts from our n items. So in the worst case, this would give us n log n time complexity. Another approach we could use is to define a build heap method. What build heap is going to do is it's going to accept the list of n items, and it's going to essentially construct a heap from those n items. Now, we know that we're storing our heaps as one-dimensional lists, so we can just assume that, for example, the first item in our list is now going to be the root node in this heap. This is going to maintain our heap structure property, but obviously it's likely going to not uphold our heap order property. So then we just need to write some code that is going to establish the heap order property, and we can do this by percolating down from each internal node to establish the heap order property. And in this case, the time complexity is going to be linear in the worst case, which is better than our initial approach, which was going to be performing n inserts. So let's take a look at an example. Suppose the list of n items to heapify is this here. So we're going to immediately construct a heap from these n items where 150 is the root, 80 is the left child of the root, 40 is the right child of the root, so on and so forth. So here is our heap here. It is a complete binary tree, but it is not in order. It doesn't uphold the heap order property. So we know that each one of our leaf nodes is a valid heap implicitly because it is a leaf node that has no children, so it upholds the heap order property, which means we need to just start one level above and do our percolations starting with our next level of internal nodes. So let's start with 110. We're going to look at 110's children, and we're going to find out, is 110 smaller than both of its children? Yes, it is, so we don't need to do anything. Then we're going to hop over to our next item in our level, 70, and we're going to look at 70's children. Is 70 less than its children? It is less than its right child, so then we're going to swap 70 with its right child. Let's take a look at an example. Suppose the list of items we want to heapify is 150, 80, 40, etc. down to 90. So we're going to construct a heap somewhat arbitrarily. We can say 150 is our root node, the left child is 80, the right child is 40, so on and so forth. And then we get a heap that looks like this. 150 at the root, left child 80, right child 40, so on and so forth. Now this is a complete binary tree. We see each level is filled and the bottom is filled from left to right. In fact, it's full. And now we need to try and restore our heap order property for this initial heap here. Now to do this, we're going to start with our second to lowest level, and we're going to start percolating items down. The reason why we're going to start with the second to lowest level is because by definition, our leaf nodes are going to be valid heaps. The subtree of a single item is going to maintain our heap order property. So let's start with 110. This is going to be the last item in our second to last row, our first internal node we're going to process. So we're going to look at 110 and we're going to ask, is 110 greater than either of its children? No, it is not. So this subtree does uphold the heap order property. Now let's move over to 70. Is 70 greater than either of its children? Yes, it is. It is greater than 50. So we're going to swap 50 and 70. So now this subtree with 50 as the root, 70 as its left child, and 120 as its right child does uphold the heap order property. Let's go over to 10. Is 10 greater than either of its children? No, it is not. Let's move over to 30. Is 30 greater than either of its children? Yes, 30 is greater than 20. So let's swap 20 and 30. So now 20 is going to be the parent of left child 100, right child 30, and this subtree does uphold the heap order property. Now we're going to move on to 40, and we're going to look, is 40 greater than either of its children? No, it is not. Move over to 80. Is 80 greater than either of its children? Yes, it is. We're going to percolate 80 down, swapping it with its min child. So 80 and its right child 10 are going to swap. Now 80 is going to be in this location, and we need to keep percolating down. Is 80 greater than either of its children? Yes, 80 is greater than 60, so we're going to swap 80 with its right child 60. So now 80 is the right child of 60, which is the right child of 10. Now, last but certainly not least, we need to percolate 150 down. We're going to find out, is 150 greater than either of its children? Yes, it is. It is greater than its minimum child here, 10. So let's swap 150 and 10. Now 150 is here. Is 150 greater than either of its children? Yes, it is greater than its min child, 20. So we're going to swap 150 and 20. So 20 ends up here. 150 is here. Is 150 greater than either of its children? Yes, 150 is greater than its min child, 30. So we're going to swap 150 with its right child, 30, to leave us with this heap structure. So 10 is our minimum item. It is at our root node. And 150 down here, our original root node ended up as the right child of 30. And here's that percolate down path that 150 took to get from the root node all the way down to a leaf node. Now here are the common methods associated with a min heap. So these would be related to a priority queue abstract data type. So we've got our constructor, we've got our enqueue called insert. Find min, this is kind of like a peek. It's just going to return the item at the front of the heap, the front of the high priority queue without removing it. Delete min, this is going to dequeue or pop the item at the front of the heap and actually remove it. And is empty, straightforward. Build heap is going to implement this process we saw here of creating a heap from n items and then percolating items down in order to establish the heap order property. Decrease key we'll talk about in a few days here. Decrease key is essentially going to update the priority of an item. So it's going to lower the current value of the item to a new higher priority value. So this would decrease the value, which will increase the priority, and move this item further up to the front of the queue, closer to the front. Increase item is going to increase the current value of the item to a new lower priority. So this would move an item in the queue further away from the front, more towards the back of the queue. And then remove an item would be to remove any item in the heap, not necessarily removing the min key at the root. So these three down here are kind of auxiliary methods associated with min heaps, representing perhaps promoting a job. This was perhaps an operating system that had different tasks that needed to be completed. Some have higher priority than others. Increase key represents demoting a job, and removing would be aborting or canceling a job. And here are some practice problems here that I recommend working through so you can get more practice with binary min heaps.